Hi, everybody, and welcome to our second speaker for this quarter's Colloquium series. I'm pleased to welcome Professor Daniel Schwartz from the Department of Chemical Engineering at the University of Washington. Daniel is director of the Clean Energy Institute and is currently the Boeing Sutter Professor of Chemical Engineering. He received the PhD in chemical engineering from the University of California, Davis in 1989. He's a fellow of the Electrochemical Society and has been recognized for his contributions by awards from the NSF, Department of Energy, Electrochemical Society, and others. And he's especially proud to be this year's recipient of the Marcia Landolt Grad Mentorship Award from UW. He served on the Technical Advisory Board for Washington State's Energy Strategy and is a current board member of the Washington Clean Tech Alliance. His research explores the transport and reaction in electrochemical systems, including the performance of complex electrodes used in energy storage and conversion. So please join me in welcoming Professor Schwartz to speak to us today.
Thank you. Thank you. Can everybody hear me? Yeah, it's working? Perfect. Well, it's really a pleasure to be here today and actually talking about my work. It seems like I've been going around as Clean Energy Institute director talking about chemists, physicists, material scientists. And so this is really new work. I think I saw the email where Matt sent to CoMotion all the intellectual property stuff so that it was sent out. And so it is really new work that has not been published. So it's really a pleasure to be here today to talk about it. Now, I think we all know batteries are a big deal. It's a big deal in transportation. These are slides that I've adapted from Dave Howell, who runs the transportation, the Vehicle Technology Office for DOE, on the growth through the last few years of lithium-ion and nickel metal hydride and traction batteries. That's about, we're looking in 2013 at a couple $1 billion worth of batteries going into vehicles. If you look at grid and some of the projections that are going out now for grid scale batteries, you know, if you look just a few years out, Lux is saying $100 billion of grid batteries. A few more years out, Boston's consulting group is saying 400. A few more years beyond that, $600 billion worth of batteries. So this is projected to be big business, both for vehicles and for the grid. And this is being driven in part by the fact that lithium-ion batteries are dropping at about 14% in price per year. And we're just driving down towards more and more viable, economically viable applications. This is a classic engineering outcome. It's manufacturing efficiencies. Engineers learn by doing, and the more we do, the better we get at it. And so there's fast learning going on in the manufacturing side of batteries. Now, there's also new chemistries, and of course, when you look at the battery challenge, first thing up always is inexpensive, and we just said that the prices are falling. So that's a good thing. You want more energy, and so if you look at a plot like this, which is specific power as a function of specific energy, largely the energy is pushed by chemistry and design. How tightly packed can you get the electrodes without it burning? So how thin can the separator be? That's a design issue, but the chemistry, each of those bars is a different kind of chemistry. And so when you talk about going from a nickel metal hydride to a lithium, you're moving to a whole new regime of energy density. So largely that axis is driven by those two factors. And for all of these, I'm going to say safely, because batteries are anomalously challenging things to deal with. When you look at combustion, the energy in the gas tank, all that energy is separate from where the chemical reactions are taking place, and you just flow what you need into the chemical reactor, your pistons or your boiler or whatever. In a battery, within the thickness of a hair, you've got a strong oxidizing agent and a strong reducing agent. So small things can go wrong. So there's a lot of work in design around, if you get a defect, can you make the separator melt so that it's a self-regulating sort of internal system so that it shuts down the current flow in the battery? But you don't have the flexibility of, in a lot of batteries, like lithium-ion, of separating the oxidant and the fuel. When you look at more power moving up that way. There's a lot of design issues, and the shape of those curves, for instance, for the lithium ion, is a design issue. If you want a lot of power, you can make the electrodes more porous, more open, but then there's less material to store energy in there, so the energy goes down as you enable more easy transport and reaction within the structure. So that shape is largely dictated by this trade-off in design. What we're interested in, of course, is, oh, and I would also add in there that shape is largely dictated by very simple sorts of standard tests, standard charge, standard discharge curves. But real batteries undergo very complicated use profiles. They're very path-dependent devices, and how you use them is really important. And so I add in here, the goal is that we could do operations that expand the curve. So for instance, I show the lithium ion, especially in the high power region, that if you're using it for short bursts of high power and then it's relaxing, you can use this path dependency by understanding what's going on in that battery and expanding, using the operational controls that you have to expand the window where that battery can operate. And so that's really the crux of what we're looking at today is to try to have good enough diagnostics so that you can control under the dynamic environment that real batteries are going to experience in the course of their path dependency and their lifetime dependencies. All right, so let's do a thought experiment. Let's pretend a power plant had a big box around it, and all you could measure coming in was the natural gas flow rate, so you get the standard cubic feet per minute of natural gas flowing in. You can measure the apparent power coming out, and maybe you can put a thermometer in the smokestack. Everything else has to operate without you doing anything. You get to control it by controlling that valve on the flow rate based on the measurements that you're getting on the outside. Now, if that was how you operated a power plant, you could know all kinds of things about the power plant, like the chemistry. The main reaction is taking methane and burning it to make CO2 and water. You could know that there are side reactions, like we were going to be regulated on the NOxes that are produced in that power plant. You could study the heck out of the boilers, understand how boilers work. You could look at how turbines work. You could understand all the heat transfer in there as individual components. But then you put it together as a system. And now you have to operate that power plant with that level of diagnostics and all the physics and chemistry hidden from you on the inside. How much more expensive would a power plant be? What do you think? More expensive? Less expensive? The same? Oh, it'd be more expensive. I won't even wait for the rhetorical answer to the rhetorical question. How much more over-design would you have to do for safety so that these things weren't burning and blowing up? If you want it to last 40 years, that boiler is going to have amazingly thick walls because we can't measure the pressure in that boiler. We can't look for slag. We can't knock the slag out of the boiler. There's all kinds of things that we would hugely over-design for, and then we would operate it. How would the operating window look? Shrunk way down. Our ability to ramp up when there's demand and ramp down when there's not demand. We would have much slower ramping rates. Everything about this would be a much more expensive proposition, a much more challenging control, operation, and safety issue. Well, that's really the situation that we have with a battery like a lithium-ion battery. And so typically on your cell phone, the control chips and stuff will have a temperature measurement, voltage, current. That's pretty much the standard that you get out of that battery. So as the load changes, you can measure voltage, current, and people study the heck out of the chemistry, like the main negative electrode reaction if it's a carbon electrode, the main positive electrode reaction if it's a lithium cobalt oxide electrode. We study these in a reductionist manner a lot, but the way the whole cell operates, it's critical because tiny bits of dissolved cobalt, for instance, over the lifetime gets over to the negative electrode, where it can lead to degradation of electrolytes at those potentials of that electrode. And there's small parts of the system that we have to engineer, and just knowing the degradative side reactions, the rates of ion diffusion and electronic migration and all that stuff as individual components doesn't make it a lot easier to control the device when the only sorts of diagnostics, the standard diagnostics, are V, I, and T. So what are the consequences? Well, there are real consequences. This battery, do you think there's a more important battery in use than this battery in a Boeing 787? Not many more use. Do you think that they have an expensive enough system where they can have the state-of-the-art diagnostics and control? Sure, they have that possibility. It still burned, and it put a fleet behind for months and months. That is hundreds of millions of dollars worth of consequence for a local company. And so there are real consequences for this inability to go in and to do the equivalent of seeing what the boiler pressure is and understanding all the things on the inside. Now, we do have the ability to go and probe the internal states of batteries. For instance, this billion-dollar synchrotron, it's great. You can look at a whole cell in that synchrotron and monitor, for instance, the states of the individual electrodes as they're operating as a cell. That's what Jerry does over in physics. He's a beam scientist. And the nice thing is that Jerry is actually helping us do this right now on campus. This is part of his research, is bringing beam science into the laboratory. And so now we have version 2 of his lab X-ray absorption fine structures instruments here, and he started a company. And I think this is going to be a huge accelerator for research, where you don't have to go sign up to get to a synchrotron, wait for 6 months, have 1 week to do your experiments. We can now, if you're a battery scientist, go into the basement of the Molecular Engineering and Science building and get spectra that overlay the beam 20 at the advanced photon source, which was the lab and the lab X-ray absorption fine structures that he does here. So that's one way, but that's not a $250,000 instrument is not a useful sensor for the battery in your cell phone or in your Tesla. So there are other ways that you can get at this. Venkat Subramanian uses model predictive control, and he tries to use really accurate models. He's a very good applied mathematician, figures out ways to make full physics models accurately and quickly compute, so millisecond compute times. So you can do on-the-fly sort of parameter estimation and control, doing things like this. If you're trying to do a fast charging algorithm for a lithium-ion battery, avoiding internal states that are dangerous. This negative going standard fast charge, that's a state that for electrochemical reasons can be dangerous to the health of the battery and can lead to fires. And so you can predict these internal states at each electrode and all the physics and control around avoiding those states. So if your model is really good and you can update your parameters effectively, this is a pretty good way to get some insights into what's going on inside of the can or inside of the pouch. The problem is that it's still updating and doing parameter fits of 20 or 30 parameters based on V, I, and T. And so there's just not a lot. V is integrated over 2 electrodes and everything happening between. I is the sum of all the physics of the battery. And so there's a lot of integrated stuff that goes into that. So sensitivity is always a challenge. So what our approach is to do electrochemical impedance spectroscopy. And the linear response of the system is widely studied for a long time. But what we're looking at then is perturbing the battery with a modulated current of some amplitude, delta I, as a function of time, and measuring out the voltage response. We Fourier transform it. We get out, well, the input parameters, the magnitude of the perturbation, delta I, the frequency of the input perturbation, omega 1, and out will come the complex Fourier coefficients, which will be related to impedances, right? The V1 will be related to the standard linear impedance. V2 is the second harmonic. It's the nonlinearity speaking to us in the battery. And V3 is also the nonlinearity. And so the impedances that we're going to get out are going to just be pure frequency dispersion functions at the first, the second, the third harmonic. So here's what it looks like if we take a lithium-ion battery. It's a 750 milliamp hour lithium cobalt oxide battery with a carbon negative electrode, held at a 3.8 volt state of charge for that battery, room temperature, and we modulate the input current. And here I'm showing the magnitudes of the current, of the transformed current, as a function of K, the harmonic number. This is for an input frequency of 1 hertz. So we're oscillating the current at 1 hertz, and the current comes in. We see that the magnitude of the Fourier coefficient rises linearly with the delta I, the modulation potential. That's what we'd expect. Coming out is the Fourier spectrum of the voltage for this battery. And we can see at the first harmonic, K equals 1, we have this roughly, it looks linearly growing peak. By the way, we've just offset them so that you can see the peaks. That's just not, it's not a natural offset. They all have 0 baselines. And then at higher harmonics, K equals 2, K equals 3, and so on, we can see growing as we increase the modulation amplitude. We see a growing second and third harmonic at twice the frequency, 3 times the frequency. We can even see as we go to higher amplitudes, 4 times the frequency, 5 times the frequency. There's these nonlinear harmonics. Just these spectra tell us something. It tells us that this system is stable to the finite perturbations we're using. So one of the things that you always have to ask is, if I perturb something with a finite amplitude perturbation, does it jump to new states? For flow, that would be turbulence. For this system, it could be a full spectrum of different features, and the fact that we see discrete harmonics says this is a well-behaved system. I've actually done a lot of different kinds of nonlinear modulations of electrochemical systems over the year. This has been a universal trait of every electrochemical system I've looked at, is that they have been stable to finite amplitude perturbations. Let's see, so what else can we learn by looking at that? Well, let's start looking at those peaks individually and their dependence on amplitude. If we look at the first harmonic, K equals 1, and this is the amplitude of the current modulation. This happens to be the real component of the voltage response. There would be a similar one for the imaginary. They follow power law type relationships. This is kind of akin to the susceptibility, the linear and the nonlinear susceptibilities in optics, where you can get the polarizability has harmonics depending upon the amplitude of the field applied to the sample. This is a little different because that's a fundamental trait of matter, and this is a system parameter. But we can think about them in some of the same ways, and I'm going to show you some of the physics. There's some interesting parallels in the physics. But anyway, here's K equals 1. As we increase it, the voltage modulation of both the real and the imaginary components rise linearly until we get to the higher values and it starts trailing off. And we're going to just look at the leading order solution. That's why I say V is about equal to zk times delta I raised to the k power. So the k is 1 in this case, so it's linear. And we're going to use values to get the slope, which is going to be the impedance, in this range of 100 milliamp modulation to 200 milliamps, just because when we go to higher frequencies, our signals are smaller, and that gives us good resolution over a wide range of frequencies. So it looks like here we could go to much lower modulations, at least for the linear component. And most people who do linear impedance are doing it down in this regime. But we want to excite nonlinearity, so that's fine for us. So let's look at the second harmonic. The second harmonic, by this power law relationship, we'd expect would go with delta I squared. And that's more or less what we're seeing here. We see the curve is roughly parabolic. I've multiplied that curve by 100-fold because this is a little tiny signal on top of a big linear response. There's a little tiny nonlinear response. And so the coefficient of that polynomial is going to be Z2, the coefficient associated with the second harmonic of the nonlinear response. And then if we do the third harmonic, K3, we see it starts out lower, but it grows cubically. And there we go. And so the coefficients in those regions that I'm showing you for K1, K2, and K3 are going to be the frequency-dependent dispersion coefficient. So our experiment is, let's vary the frequency of the excitation, and let's listen to the linear and nonlinear response of the battery. And here's what that looks like for the linear impedance. You could find curves that look like this for a Nyquist plot, the real part of the impedance. I show it in terms of the variables we're modulating, millivolts measured, milliamps. That's just ohms, of course. I'm talking to electrical engineers, for goodness sakes. But just so you know, batteries are low impedance devices. See the 10 to the minus 2 over there. And that shape is pretty typical. The characteristic frequencies I'm showing you are giving you a sense of different time constants within the battery itself. Low frequencies off to that side are transport processes within the battery. The arc, if there's 1 or 2 arcs, is related to charge transfer typically. The offset from 0 is related to resistance in the electrolyte as we go to high frequency. There's a bunch of stuff we can learn from the linear impedance. The way we normally interpret it is kind of the way I was just saying. We use we'll use a linear, sort of a circuit, equivalent circuit diagram to figure out how many degrees of information are contained within those arcs and how they're related. So for instance, our charge transfer, I can show you in a linearized model of the physics of a battery where our charge transfer comes from. And it's got a bunch of lumped parameters together. I can't separate them out from the linearization. And so I can't find out everything I want to know about charge transfer in the first harmonic. I can show you the conductivity of the electrolyte, the geometric factors that go into the resistance of the electrolyte over there. And some electrodes, ZW is the Warburg impedance, that low frequency stuff is a transport-related impedance. Capacitance of the double layer, we've got the interface between an electronic conductor and an ionic conductor. That interface will have a capacitance that we represent by C double layer. And so each electrode will kind of look like this. But a lot of times you only can get these 1, 2, 3, 4 bits of information. But that's better than voltage, current, and time. We're now able to start poking at different physics that's going on the inside of that battery. And that's useful. It's kind of like taking my power plant and now being able to put a microphone next to the burners in the boiler, a microphone next to the turbine. And I bet that if you were listening to those, you could hear differences and there would be something useful that you could do about expanding the scope of how you could control that power plant that I started in my introduction with. And so people have done a lot of stuff. And these models, by the way, when they use them a lot, like the car companies, they can trace the full 99% of the variance in a driving cycle, the voltage-current relationship in a drive cycle for a vehicle battery. 99% of the variance that you see can be captured by this. So you can do like real-time parameter estimation on this and stuff. And you're going to get a lot of insights into the battery as you're using it for your vehicle, your grid. The problem is 99% is not good enough. Think about batteries. We want them to last, 10,000 cycles, right? That's a pretty good cycle life. That's a good cycle life. We want them to degrade no more than, typically the warranties are 70% of their original capacity, and then you throw away. So the amount of net chemistry that takes place in 10,000 cycles compared to the amount of the bad side reactions and stuff that degrades the battery, it's a 0.1% or less problem that we need to be able to detect. So 99% is not good enough. Of the most reversible, most linear, most well-behaved part of the battery, 99% of a battery is well-behaved. It's that dang 0.1% of the battery that's badly behaved that leads to fires, that leads to degradation, that leads to things like that. But nonetheless, I want to show you that you can do interesting things with that small bit of extra information. Here, for instance, is a IEEE paper looking at, it's a highly cited paper because they're doing Bayesian, using a Bayesian framework to do predictions around measurements of this R charge transfer plus R electrolyte. So the sum of those two is a strong parameter for prediction. And So this is showing the remaining usable lifetime. 70%, I said, is a typical number. And they're making, this was a long-term study, DOE funded, to look at the degradation of enough batteries that you could do statistics on it. There aren't very many of those in the public domain, data sets like that. And then looking at times as the battery is degrading and doing predictions of when, getting a probability distribution function of when the battery is going to hit its sort of warranty level of 70% based on, you know, sort of half of the lifetime of the battery or a little further out, and narrowing in. The battery actually died somewhere around 62 or 63 weeks of use. How many grad students want to do experiments for 63 weeks to get the one plot? Not many, so that's why there's not that many of these, and people are really working hard to have accelerated tests that are authentic, but it's not necessarily out there yet. But that gives you an idea that there's more prediction power as you start poking on the inside, just like you could imagine with the power plant. Okay, so now I'm going to tell you a little bit about what we do with those nonlinear signals. And I'm not going to go into much of the math that we do to process them. You've seen most of the basic things, but what we're expecting is that the nonlinear impedance, those peaks that were less than 1% of the total output signal, it's not routinely measured. I'm going to show you the first ever full spectrum nonlinear impedance spectra for lithium-ion batteries. But there are important things that are embedded in, for instance, the second harmonic. It is sensitive to symmetry breaking, just like the hyperpolarizability, the susceptibility at second order. If you have a crystal structure that has high symmetry, you don't get a second harmonic. The same is true of this battery. If you have a symmetric cell where it's exactly as easy to charge as discharge at its state of charge, if that's true, you get no second harmonic in there. And so when you start seeing a second harmonic, it means there's asymmetries in how the two electrodes are. There's a lot more information to that than that, but that's one easy thing that we're gonna pick up as we start looking at this and comparing it to modeling. Degradation, I mentioned, involves these tiny, small, irreversible chemistries. And capturing 99% of the variance isn't good enough when the things that matter are these irreversible, non-ideal stuff that's happening at 0.05% of the net chemistry that's going on. Batteries are pretty well behaved. And the challenge is that to interpret these requires more insights into the physics. You can't just plug an equivalent circuit in. And I think for my community, that's been one of the things that has held it back the most, is that people are comfortable with the equivalent circuit analysis. They're not necessarily as comfortable with the full physics modeling necessary to get into the nonlinear dynamics. So let's take a look at the first ever reported sort of second harmonic impedance that's coming out. And here we're now taking, remember, we're dividing by the amplitude squared, so we get this millivolt over millamp squared, or ohms per, in these units, millamps squared. And this is the imaginary and the real. It's all in the first quadrant, just like the first harmonic was, like the regular linear impedance. It's a smaller signal, and you can see the dynamics again through a couple of characteristic frequencies. That's what it looks like. If we go and look at it, an important thing here, we saw it in the spectra at 1 hertz. There's a measurable second harmonic. It's comparable to the third, and that measurable Z2 indicates asymmetry in the ease of charge and discharge. And what I'm going to show you is that all of the standard models for how these batteries work, because they've used V and I and linear impedance, they're not sensitive to that breaking of symmetry. Doesn't matter, so they've always assumed it was symmetric, and this is evidence that there's a breaking of symmetry in a well-functioning battery that hasn't really been detected in a whole cell before. So here's the third harmonic, and again, now we're dividing by delta I cubed. It's got these weird units, real and imaginary. We see it's mostly in the third quadrant with a little dip into the fourth quadrant. There's interesting stuff going on here, and it's all coupled to the transport, the reaction, and everything that's going on, and we should be able to, through modeling, separate these things out. The problem is that right now, I can't tell you very much about what this means. I can see features, and I could do pattern recognition on those features. I could start correlating good-looking shapes versus bad-looking shapes, things like that, but I'm not pulling out the physics of what's going on in individual electrodes, because not everything is equal. Some reactions are dangerous for the health of the battery. Some are not safety or other related issues. So we need to do proper modeling to interpret this. And I'm not going to go into the full model, but I'll tell you a little bit about what a pretty good physics-based model for a battery looks like. First off, the batteries we're using are rolled cells that look kind of like that. And so they're just planar sheets. And so we're going to represent the battery mostly as a 1D cross-section through those planar sheets. So we've got a positive electrode, a separator. So you've got this positive electrode on a copper backing, the negative electrode on an aluminum backing. You coat them, you put a layer between, you roll them up, you drop some electrolyte into it. Okay, and so we have a porous electrode. That's the negative electrode will be a carbon electrode. The positive electrode on that side will be, for this case, lithium cobalt oxide, one of the high energy density batteries, the one that burned in the Boeing plane. In the middle is a separator, which is a porous polymer that tries to keep it from short circuiting, but allows ionic transport through the middle of it. The physics of the electrodes it's porous electrode theory. So we have an effective porosity, we have tortuosities, transport through both of these two porous electrodes. But embedded in there, we include the physics of interparticle transport, because a lot of the low frequency stuff is getting lithium in and out of the solid state. And so we have in parameters like the size of the particles that are in the slurry. And a model like this, which is known as the P2D, pseudo two-dimensional model, because it's got particle dimensions and cross-section info, has roughly, depending upon details of what you do, maybe roughly 20 physical chemical parameters for charge to represent charge transfer, to represent diffusivity of ions, conductivities, and maybe 8, well, could be from 5 to 10 unknown, or 5 to 10 geometric parameters that you could go in and measure if you knew them for most of these electrodes. So that's what is in a typical model. We're going to discretize this, and Matt will solve it in a very efficient analytic numeric form. So we compute in the frequency domain, so we can directly get out the Fourier coefficients that we're measuring here. But the details of that is going to be given, it'll be given in the paper that will come out from this. We're going to adapt, basically, this model. We're going to expand the first representation of this full physics calculation of the linear impedance. We're going to expand that model to incorporate the nonlinear contributions. All right, so let's take a look, and now we're going to mostly look at shape, because these are on a per meter squared basis, because the computed it just has the cross section. And so we're going to look at the shapes, and we're going to compare the linear response for the experiments and the computed. There's a couple of things that you can see. There's some error in the shape. For instance, at the high frequency, it's coming kind of in at 45 degrees there, and here at the higher frequency end, it's kind of blobbing in more straight down. We see that the frequencies are off where they fit within this. So the dynamics that we're putting in using standard parameters, these are the parameters people usually use because they're thought to be the best representations. A lot of people model these kind of batteries. It's most common, really, in the literature on modeling it. We're harvesting the most common standard literature parameters, and now we're looking at them for our battery, and they're off. So we could do a best fit, even with the linear contribution. We can see that we're a little bit off. And so we could do best fits on those parameters, get 5 or so lump parameters, more information, and do a better job of fitting this, I think. So now when we look at the second harmonic and we look at the standard parameters, big differences, big differences. The second harmonic in our real battery that we measure is substantial. We saw that second harmonic peak growing at 1 hertz, and it's substantial. There is virtually no second harmonic in the computation when we have got these parameters. And that is largely, it's not just that I've created the axes to do this. It is a very small signal. And the reason is that the standard model and the methods that they've been using can't see the symmetry of the reaction. And we capture enough of the variance of the signal to when we just assume symmetry and charge transfer on both electrodes, that effectively we've squashed the second harmonic with the standard parameters when we use them in the literature. And so there's a lot we can do. In fact, if I just change one parameter, I can start moving towards a best fit. Now, we're not going to do best fits because this is really new data, but we will eventually get to doing best fits of parameters and seeing how much information we can glean about the physics inside the battery. But let's just do one thing. Let's add asymmetry to the negative electrode, which we know is the main contributor to the linear impedance. So let's put asymmetry in that. And now we start seeing a loop that has some traits. That loop goes a little bit into the second quadrant of the Nyquist. That's a little different. This one kind of comes straight down along the imaginary line. But we can see that as we break the symmetry by making the negative electrodes cathodic and anionic charge transfer be asymmetric, 0.65 and 0.35 instead of 0.5, 0.5, like the standard model, we start introducing some of the feature shapes that we need. So there's more information in here than we've ever been able to really glean in the past about this. So asymmetry in a single charge transfer reaction improves the shape, though it's far from a best fit parameter. All right, here's the third harmonic spectrum, the Z3 spectra using the standard parameters. I'm kind of amazed by how this works. I mean, the high frequency, we saw the looping from the third quadrant into the fourth quadrant. It has the same kind of looping into the fourth quadrant. Again, the time scales are off, and there's a little bit of a high frequency feature in the computed that is different than I see over, in the low frequency. I mean, my low frequency is starting to go negative. That low frequency is kind of shooting off in the different directions. So there's a bunch of low frequency transport things that we're getting wrong, but we're starting to be able to probe in new and unique ways through the nonlinear dynamics of the battery in very measurable and easily reproducible experiments, new physics that's being illuminated by this. So that's kind of where we're at this point. We've got data, we have models, and we have now extra information about what's going on by looking at the linear and the nonlinear harmonics. The low frequency stuff has thermodynamics and transport in it. The middle to high frequencies have information about the charge transfer in it. The highest frequency in the linear tells us about the electrolyte resistance. All of that is tied into those 20 parameters in complicated ways. And now we're sorting through how do we find and what is our parameter sensitivity so that we can really begin to understand what's going on there. So let me just conclude by telling you where we're at today. Nonlinear impedance is clearly measurable, and it is complementary to the linear response. We get information like symmetry out of there. And from that, we can see things like the standard lithium, cobalt, oxide, carbon electrode parameters from the literature are clearly inadequate when you start looking at the less than 1% of the variance in the data that you can get out from a method like this. We're starting to probe new physics. And that's especially just hits you over the head when you look at the symmetry of charge transfer as something that is going to be a new thing. And it's an important thing because a properly functioning battery, if it's a rechargeable battery, you want it to be able to recharge exactly as easily as it can discharge, so that it has this nice ideal reversibility. And probing things like the breaking of that symmetry is telling us very important things about reactions taking place at individual electrodes. And then we expect that with this additional information, we can start having parameters that will be better predictors of things like the remaining usable life, the dynamics of having a real-time meter saying you're stressing the battery now, and being able to put that into your economic decision-making. It might be worth stressing the battery and reducing the remaining usable life by a certain amount because the income you can generate today, right now, is so high, but you want to do that without moving into dangerous states. And so being able to open up the energy power window by having a real-time diagnostic, I think is going to be really an important contributor to the economics of how we use batteries into the future. So I just want to thank you and say that Matt did the work, and Hannah, I don't know, is Hannah here? No. Hannah is working with us as a co-advisor in the IGERT, Data Sciences IGERT, that Magda is leading. And so she's been helping us as we start thinking about this next step. Now that we have measurements that we believe in, how do we collect data and glean information and insights? Matt was a recruiting fellow through the Clean Energy Institute to come to the UW, and he's been supported by a Department of Ed Gone Fellowship as well. And so with that, I thank you and would be happy to take questions in the remaining time.
Questions from our audience? I have one. So I'm curious about the energy cost of making an extra measurement of the battery, and particularly if you imagine a grid scale battery or the battery in your electric car, you might have to draw a lot of current in this special way in order to make the measurement. So, where do you think that trade-off is, or is there a benefit that outweighs the energy cost of making the measurement?
Well, so we do perturber on the zero state. So it's off. There is a small, because of nonlinearity, there is a small net change in state of charge, which is known as the Faradaic rectification. So you get a small bit of positive or negative change in state of charge in doing the measurement, but it's small. I think the big question would be in the power electronics and things like that. And I don't have a good answer because I really think we're just at the very edge of seeing what more we can do. Now that we have these methods and we have a model to predict, we really don't know how much genuine, can't put a dollar value on how the extra insight is going to let us open the operating window up and what that would mean in terms of revenue. It's a really complex question, sort of the connection between how we operate in the economics. And I think that some like Miguel and Daniel Kirshen would tell you there's a lot to figuring out sort of optimal economic operation of these things. So that was a long answer. They say the answer is supposed to be exactly as long as the question, if you're doing a good job. I gave a long answer to a short question, and the short answer is not sure yet.
Well, what lessons were learned from the 787 battery?
Manufacturing defects were I think the main issue. They made a design choice to go with the highest energy density batteries, which are or some of the highest energy, which means that you're taking more risk, and they wanted to reduce weight. I think that my understanding, and I have no insider insights, I need to provide a caveat there. My understanding is that there were manufacturing issues which of course you would want a diagnostic that could test that, right? I mean, even if it's just at the factory floor, you would want to be testing for any of the sort of fault states that could lead to problems. And so I think that it's part of the same story, just on the manufacturer side.
Other questions? Yes.
So it will take some time to do the research, and then you have to publish, and then people have to discuss and accept. How long time do you think it will take before we have the courage to put this in operation?
Yeah, so can you say it again so that I can repeat it accurately? So it'll take time. So the first part of the question was, it's going to take time to complete the research, to get it published, to have it accepted in the community. And what was the second part?
And then, how long time in total do you think it will take before we have the courage to use it in operations, in real $1 million type battery?
Well, so I think that so the second part of the question was, and once that happens, how is it going to start getting adopted into the marketplace and used? And I think that the question about things like detecting manufacturing defects, it's a pretty low barrier to using a new diagnostic method as part of your quality control, quality assurance. So that, I think, is a much lower barrier than using it in a measurement and control scheme, in a vehicle, in a grid application. And so I would expect that would be part of the acceptance and adoption, would be through people that are manufacturers, the LG Chems of the world, the Panasonics, the A123s, the ATLs. These companies have teams of people kind of like me and my students, chemical engineers, material scientists, trying to do state-of-the-art tests. Those are the kind of companies that are buying Jerry Seidler's X-ray instruments so that they can start probing these things. And so I think that it will be comfort level there. Part of also the business model of batteries is a lot of the people that buy these batteries, I meant to bring down a battery pack from the hybrid buses that we just got from King County. But A123 sells the battery and the control system for those hybrid bus batteries. And so the people that are putting the systems in, it actually matters that the manufacturers are comfortable, because you want them to embed it in their battery management systems and things like that. So I think there will be a natural progression from test to the battery manufacturers' BMSs to then the next level of control layers that will just be a part of a control action for the utility, the vehicle controller system, that it will be coming out of the BMS and the battery. So I don't know that exactly answers your question. I didn't give a time. I would say 19 months. No, I'm just kidding. But things don't ever go as fast as you would like. But I think that what I showed you, that people are going to be very interested in it. They're going to see it. They're going to see that there's new information. And anytime you can get new information, these batteries we're still pushing for $300 a kilowatt hour. That isn't a very expensive power source. So people that can get more insights, into what's going on in their $300 per kilowatt hour stuff. By the way, that's like that amount of energy is, less than a cup of gasoline way less than a cup of gasoline has that much energy in it. So a cup of gasoline today costs what, quarter or something, and these are $300 we're trying to get to. So there's a lot of impetus, I think, for new insights that let us push that operating envelope. Another long answer. It was a longer one.
Any last questions?
Matt, I could do one.
Sure.
So if you take the semiconductor industry, they typically don't build until they model. So if you take the battery industry, can you give us a perspective of if that's the case? I mean, do all these companies, would they do extensive modeling cycles before doing it? And I imagine the answer is no. And if it is no, what is the underlying reason for it? Is it because these gazillion parameters that go into these models have not yet been kind of, you don't know the experimental values, like say the mobility of electrons and holes are very well known in semiconductors because experiments were done, 60, 70 years back. Whereas those kind of quantities are not known in this field. What is the bottleneck?
So the question was, do they do design build in this business, where they spend a lot of calories on doing a good job of modeling the system before they go out and build a fab or do something like that. And what I would say is that one of the things the semiconductor industry has going for it is that, well, they're a high margin business. At least they hope they are. A lot of time, early on in the cycle, they're a high margin business as they're bringing these things to bear. And silicon properties are very fundamental properties. LG Chem's lithium cobalt oxide has a little bit of this and a little bit of that extra. There is so much material science tweaking to the formulations that I think that the fastest route has historically been test materials as individual things and slap them together as a cell test and then go up in scale. That it's a faster design build cycle for them is through sort of empirical steps. And so it's not to say that every one of the major companies doesn't do design work, but keeping up with it, getting all the parameters that are necessary. They are fundamental parameters associated with diffusivities of the ion and the electrolytes. And as they tweak the electrolytes to make them more stable, those all change. They have to make measurements. The thermodynamics, we don't know how to predict accurately the thermodynamics of these materials. And so you already start having to do a measurement of just the thermodynamic states of these materials to get at what will just be the zero current voltage in the cell. How would you predict it? So it's a challenge. My colleague Venkat Subramanian says there's a Nobel Prize for accurately predicting the equilibrium potential of some of these complex metal oxides with defects and dopants and whatnot. People compute it, but they just don't compute it accurately. So there's a lot that is left from first principles up to the design and modeling that just makes it hard to get all the parameters you need accurately in a pure sort of ab initio manner for design. Other questions?
All right, with that, thank you very much for taking an ideal voltage source and showing us that there's a lot more to it than that. Thank you, Dan.